Mike, and I'm gonna let him say his full name in a minute here, but Mike comes to us from over 30 years of experience working in hydrogeologic and geochemical studies in the Beto zone, which is for you that might not be that familiar, the unsaturated zone above the groundwater. And today he's here to talk to us about managed aquifer recharge. And he's worked on over 60 surface water spreading projects, including riverbank infiltration and working in riparian habitat restoration, and also looking at implementing stormwater strategies and capturing that water and recharging it back into the ground. So a few of us here, Andy and Mary, we met Mike at a conference in San Antonio last year on that the National Groundwater Association put on back in last April, and we took his workshop. And when we started kind of delving into this, we knew we had to get him up here, and we're really glad we did. So I'll turn it over to Mike. Feel free to do more introductions.
Thanks, Jenna.
Yeah.
Yeah, so this talk is I didn't know exactly who would be here and what your background was. So this is a fairly general overview of managed aquifer recharge and what some of the tools are and the methods and how people are doing it. So feel free to interrupt me at any time if you've got questions. No worries about that.
I need to click on this.
Okay.
Yeah, if you take it off that Zoom bar.
Take it off what now?
Yeah, it was just on the Zoom bar at the top.
Is it going to work now? Let's see. Yeah, okay. So managed aquifer recharge, it's been around for a while. There's a couple of it, let's just say cultures from about the 700, 800s that were practicing managed aquifer recharge. I'm aware of these. I'm sure there was other cultures as well that were probably doing it. But amunas are a type of managed aquifer recharge that to this day is still practiced in Peru. And it was essentially the Moche people. They basically were taking the water comes out of the Andes during the rainy season and flows down the river, and they were taking that water out of the river and sending it to areas that they had discovered where it had high infiltration, and so the water was leaking into the ground and basically supplementing the springs that they would rely upon during the dry season for irrigation and at elevations that are lower. And then there's called carreos, and the Arabs, the Moors came up from northern Africa and colonized Spain. But what they brought with them also was desert agriculture, and you may have heard of canats, which are these big drainage tunnels that were developed in the Persian and the Arab Peninsula back in the early on. And so they basically took a look and they started putting in terraces and stormwater capture systems on the south slope of Sierra Nevada. And so these are basically leaky canals and diversion structures. The geology is different. In Peru, it's mostly salt and andesite at high elevations, and then it flows down into other types of rocks. The carreos are primarily over schist. And these are, what's interesting is that these are communal systems that are still maintained. There's not as many amunas as there used to be, but it's a family lineage thing. It's like a ditch rider turns it over to his son, and then they maintain the systems, and this has been going on for centuries. So an example with amunas, basically, the typical cross section is they've got these canals that are diverting high water during diverting high water when the rivers are flowing at high stage and flowing across the salt, and it's leaking in, and then they have these areas they might find where they put in retention, and the water flows in and it ponds there and it sinks into the ground. And later on during the dry season, it supplements those springs, and if the moon's not there, those springs basically just stop flowing earlier, a few months earlier. with Carreos, it's essentially the same thing, but there doesn't appear to be like these big retention structures, and that's probably just due to geology. But again, they found these ditches, or they built these ditches all along slopes, and basically same deal, except here they're, you know, and they're more metamorphic rock that's really fractured, and then it flows down. It might go to a spring that you know, has some infrastructure associated with it, like some town spring, people go get water from that. So that's an example of managed aquifer recharge that's been around for a long time. So what I'm going to talk about today is I'm going to basically go an overview of the types of what we call surface spreading methods, and then there's subsurface methods. Basins are the most common. That's what most people think about when they talk about spreading basins. There's also a lot of recharge that occurs in channel. You can do that. I'll talk about that in a minute. Leaky canals, it's a big deal, especially in agricultural areas. Flood mar, ag mar, on-farm recharge. This has been developed most recently in California. I'll give you some examples about that. Another thing that's quite interesting that's starting to happen over the last few years is putting in reverse tile drains. Okay, so tile drains have been around for a long time. French started writing about them back in the 1850s, and that's why they're called French drains. And but they've been around since long before he started writing about them. But the concept here is where you've got a bigger beta zone, you basically put in a tile drain, and then you inject water into it. Instead of pulling water and lowering the groundwater table, you're basically putting water in through these tile drains. And then there's what I call recharge enhancements: gravity drains, dry wells, infiltration galleries, wick drains. These are quite useful when you may not have as much land for a surface spreading basin, or perhaps you've got some impediments to groundwater recharge from a spreading basin, like some fine grained units that are fairly shallow and you can punch past them with a dry well. And then I'll talk a little bit about riverbank filtration, which is a form of induced recharge, where basically you're pulling water, you're pulling additional water out of the riverbed into the groundwater system. Subsurface methods. Really, there's just two: beta zone injection, gravity wells, and then ASR, aquifer storage and recovery wells. So, surface spreading basins, chuck a bunch of water on there, and it goes in the ground magically. Well, those of us that work in sedimentary basins know it's a lot more complicated down there. And so, what's really happening is that you go out and you drill some logs, you dig some test pits, and you see, oh yeah, I've got really good high permeability sands at the surface, so I can put a recharge basin down there. But you may have some lower permeability material. There may be, they may or may not be continuous until you get to the groundwater table. This is actually a cross section from a site that we worked on in the Phoenix Valley, it's called the Salt River Valley. And so when you start putting water on there, water starts flowing down. It's actually probably pretty saturated right there, but the material may be so permeable that you get an unsaturation, hits these silty sand layers. You might get some perching, and then at steady state, you might have a perch zone here, some multiple zones, and then the regional water table starts to rise, and eventually, you run it long enough, these will merge. Now, the key thing though in basins is you never want this perch mound to rise up into the top of your basin, because if you do that, you will basically negate all the hard work that you did, because you won't get vertical flow at a unit gradient. You will start getting lateral flow at, you know, a gradient of 0.1, 0.05, whatever it is. And so your recharge rates will go up really quickly. So that's a kind of a key thing that you need to look at when trying to site basins. I'm not going to go into any of the technical stuff. We can talk about that tomorrow. As we meet. In-channel recharge. This is typically used in ephemeral stream channels, or where the water table is below the channel in the canal. So it's a losing reach, right? So if you can have, if you can increase the amount of water that's sitting on that channel, either through the amount of time or increase the head, you're going to increase the recharge. So an example here is putting in weir wells. This is in a drainage in southeastern Arizona. And when it storms, there's actually a detention basin up here, it meters out slowly, and these fill up these walls. Before the walls were put in, the water was just run down, and it's basically holding onto that water for a little bit longer and allowing more to sink into the ground. If you double the amount of time the water sitting there, you double the amount of recharge that may be occurring in that channel. It's pretty simple. I've never, I've seen this a lot of places, okay? It's extensively used in northeastern India. They have all these check dams that they put up everywhere to capture water during the monsoon season, and it's basically, that's what they're doing, is they're slowing the water down. The Native Americans used to do this, they used to call it trincheras. They put these little check dams and little drainages in the mountains in the Sierra Madre, and that go up into Arizona. And it basically just increases the recharge. It has erosional stability. The CCC did a bunch of check dams back in the 30s in Arizona. I've never been able to find out why, but there's thousands of them in certain areas. So very common, used worldwide, sand dams, berms. Here's where they just basically took some pipe, actually had a recharge, an in-channel recharge facility on the Augment reservation in Arizona. And this is just pushing water up so you get a little bit more depth and you get more recharge. So that's pretty simple. And then of course, we'll talk about this a lot tomorrow, I'm sure. Irrigation canal leakage, it happens, and it's called incidental recharge, but it's recharge. There's other things you can do. This is basically a low flow structure where there was a road going underneath this bridge. And they basically just brought in a bunch of gravel and they built it up. And the net result is the water is now backed up behind it, so we're getting more recharge. And this is downstream of wastewater effluent discharge. And so this is one way that, and actually this is not correct. This arrow should be right here. This is downstream, and this is upstream right here. So this is backing the water up and basically increasing the amount of recharge that's occurring in the channel. Rock gadium structures, basically you call them leaky weirs, whatever you want, but basically pond the water up, move it around. You can, they've done stuff like tip old oxbows and move the water into oxbows so that you have more spreading of the water. Again, all in channel. And then this is kind of the classic design I like to talk about. This is the Santa Ana River. And this is in Orange County. It's, I think, the second largest, the LA River, and then the Santa Ana River is the second largest river in Southern California. Basically what Orange County has done, and the majority of this water is treated effluent. So it's an effluent dominated stream. They put up what they call T's and L's. So here's your L, here's the T, and they just get a guy out there with a dozer. He pushes up a berm and it's maybe about 2-3 feet high. And the water then has to flow around it like that. I didn't spend most of the time going back. But so the water has to take the circuitous route, and basically you're backing water up here. So you're increasing the head in the channel of the water by, a foot to 2 feet, and that increases the recharge. And they've documented, they obviously think they increase enough recharge that it's worth a guy to get out there with a dozer, because every time there's a big storm, this all blows out and they back out there again with the dozer. Floodmar. So this has been pushed, being pushed heavily by the state of California, because the Central Valley, if you've ever been there, it's several million acres of land, and that is their biggest water user in the state. They, I don't know what the percent is, but farming, probably still uses 70-80% of the water that's used in California, even though there's 40 million people there. And so the idea here is they've got lots of reservoirs, and so when they have a wet year, they can send those the water down. They can flood fields where maybe you have some crops, or flood fallow fields, recharge basins that basically take that water and put it into the ground. Now here, where your big advantage is the sprinkler shot, being able to capture those peak flows and knock down those peak flows, and steal the money, but that's all right. And what do I have here now? So, this issue of water rights is always going to come up. And so this is actually off your website. And so this is from, I think, 1880 something. And so this is the average precipitation. And I'm not sure which gauge this is from, but this is in Montana. And so we have obviously some dry years ranging anywhere from 5% deviation from normal down to 30%, and then you've got these wet years. Well, this is where on-farm recharge becomes important, is when you have these wet years above average years, because you've got a lot of excess water. And so if you have upstream tensions and you've got a lot of water, and when that spring freshet's coming, diversions on farmland where they're recharging on the fields, are basically doing excess irrigation, getting water into the ground. And those are your opportunities during those wet years. There's been a lot of work done on crop effects, and basically certain crops don't like it, but crops that are able to grow in sandy soils, or crops that don't mind getting the wet, like walnuts, pecans, grapes, or water plants that use a lot of water, they tend not to be as affected by this. But they're still working on this, but you can't flood your fields for 3 months, but certainly you can flood it for 2 weeks or 3 weeks, depending on the crop, and it can handle that kind of over irrigation without the roots have to get enough oxygen, so there's a limited time, but you can do it. Or again, if you have fallow fields. Now, when you start flooding ag land, depending upon how long it's been operating and how they, how much deficit irrigation they use, you will have flushing of agricultural drainage, high TDS nitrates. Pesticides and herbicides typically don't go that far, but again, it depends on how close you are to the water table, what the sediments are. So these are things that you need to think about before embarking it. But eventually, if you get enough water in the ground, you will dilute this, and that's the idea there. This is an example. Jeanette, this is the client I was telling you about, the grower. So this is an operator called Homer LLC. I don't know whether they were fans of The Simpsons or what, but so they have properties, ag properties throughout California, and we've worked with them identifying areas within each of their farms, and some of their farms don't have any good areas. They're good for recharge, and so they keep these fields fallow, and then during a big year they'll flood them. And I think last year, I can't remember what he said they got in the ground, but it's something like 80,000 acre feet. It was between 80 and 120,000 acre feet that they were able to recharge in these basins that they'd identified on their lands.
And then, Mike, are they then using that water? They withdraw?
Right. Yeah. Central Valley is completely, it's very, even though they have all these reservoirs that's coming from the Sierras, the groundwater elevations have dropped there anywhere from kind of where you are. The farther north you get, the less the groundwater elevations drop. Down the south, they've dropped a couple hundred feet. So they're in serious overdraft, and they now have a state law called the Sustainable Groundwater Management Act. It's basically cracking the whip and requiring all of the various, they formed what are called groundwater sustainability agencies. So each groundwater sustainability agency has a plan that says, I'm going to be out of overdraft by, I think it's 2040, because they have to be in sustainability. So it's causing. Lawsuits are starting, there's lots of arguments, but they're having to figure out how they're gonna do that. It's gonna be a combination of increased recharge, and then some of those areas are just gonna have to fallow fields to, or switch to different types of agricultural crops, they're less water intensive. This is an example of on-farm recharge. This is a grape grower, and basically, and I don't know what the periodicity is on that, but one of the things that you have to consider when you're flooding farmland is that there's always a little bit of drop on irrigated farmland. So if you want to actually spread the water out, and depending on how long the irrigation checks are, you may have to put some intermediate structures in, like here, they just lay out some pipe. And then here, they're actually using pipe to spread the water out a little bit, a little better, and get better even distribution, because again, it's this whole issue of keep the surface, try to wet as much surface as you can to get water in the ground. Now, the interesting thing is that a lot of people just, went out and started throwing water on the fields, but in the Central Valley, some of the soils are not that great. They might only get 2 inches of infiltration a day. Okay, so it becomes critical then to get a better understanding of what your infiltration rate is, so you can figure out how much infrastructure you actually need to put in. Because if you're going to over irrigate, you may not have your existing infrastructure, you may not be able to provide that much water, and then you're also building a bigger diversion structure where you better be sure that your fields can take it. So reverse tile drains. This is a big giant ditch witch, basically, and this actually is kind of this is provided by Lidco, which is they do tile drains all throughout the Imperial Valley. For those who don't know, they call about 1 million acre feet a year from the Colorado River go to Imperial Valley, which is like the highest place in the US, so that they can grow rice. And amongst other things, it's kind of mind-boggling, but they also have drainage problems. So these guys are mostly in the Imperial Valley, and they do tile drains to drop the water table, but now they've been putting in these reverse tile drains where the groundwater is much deeper, and so they just, dig big giant ditch, pull the water out. They've got a feeder. This is slotted HDPE pipe. If you guys have ever looked at like a heap leach pile in mining, they use that to help with the drainage. It's just got holes punched in it. It's corded. It's not corded. Yeah, I guess they call it corrugated, so it's flexible. And they just drop it down in, and then they got a guy coming behind. There's a hopper right here that they're dumping gravel into. So it's a one pass operation. They did the ditch. They drop the pipe in. They dump a load of gravel on it. I can't remember what they got. It's like 12 inches maybe. And then they come in with a little bobcat and push over the dirt back in the ditch and get done. And so in this case, they've applied this under orchards. Typically, it has to be done before you go in and you do any type of permanent crops. We've been looking at it actually in a project in Southern California where one of the areas will go under a parking lot. So it's for areas where you have other land use. And so in a place like Southern California where it's land's super expensive, this makes a lot of sense, because putting a basin there, you may not get as much water in the ground, but the land is worth $1 million+ an acre, right? So having a basin there is not as cost effective as this. And the interesting thing about this is they have jetting technology as well, that they're able to run a long tube with a jet on it to clean out the pipe if it gets clogged. One thing is, it's not clear to me yet, but I think depending on your state and whether or not you have primacy from EPA for underground injection control, this may be considered a class 5 well. It's variable, how they interpret, what the depth versus the surface area is. So it could be a class 5 well. Of course, if you can get out of that would be best. So riverbank filtration. Does anybody know here about riverbank filtration? I just gave a talk about this a couple weeks ago. It's interesting. So the first one was that we know of was put in Scotland in 1810. Basically, someone figured out that, hey, all my neighbors have been cholera, but I haven't gotten cholera because I have a well. And so what they did was they actually deliberately dug a well next to the river and started pulling out of it. And so that what you're doing is you're inducing water to flow from the river towards the well. And so there's a few of those that got put in, and you know, but most of us here of European descent, if our ancestors weren't just constantly drinking beer and wine all the time, we've all would have died. Because most of the rivers in Europe were open sewers. Okay. And so after about World War II, after there's all this massive industrialization, in addition to the pathogens, there's all these chemicals. And you know, you remember back in the 70s when I can't remember the Cuyahoga River in Ohio caught on fire. Well, that's what it was like throughout the industrialized world. And so Europe went, and primarily along the Rhine River, because there's all kinds of industry along the Rhine, they went extensively into riverbank filtration, and in fact, at this point, in between the Netherlands and Germany, probably about 20% of all the water comes from riverbank filtration. And in other countries like Switzerland and I believe Hungary, it's as high as 50%. And so this is where they're getting the water. In fact, you're not allowed to use surface water in the Netherlands because they don't allow chlorination. So they have a system that's set up where they're either using groundwater or riverbed filtration systems, and then they pull the water out and then you do UV ozonization, but they're not on use. So anyway, background, interesting. So what you're doing is you've got your surface water. You're actually lowering the groundwater table next to the surface water, and that's inducing recharge. So you're increasing the amount of recharge. Now, this could go to ag or whatever, but it's a form of recharge. This is what you most commonly see in the US is a Rani well. There was a guy by the name of Rani who developed this technique, and basically it's typically a big giant caisson. You can actually go down in some of these big giant ladders. And then they horizontally drill around the river and actually underneath the river. And so this way it's the same thing. They're inducing recharge, but they're using this random well system. And so what's interesting is that these are quite effective, quite efficient, but the retention time between the surface water and the laterals is less. So some places have to be a little bit careful. Like Sonoma County has a number of these systems, but there's one particular lateral system that they can't use once the water gets above a certain flow rate, because they found that it's in too close connection with the river and doesn't provide pathogen reduction. Now, soil aquifer treatment, I'll talk a little bit more about soil aquifer in a minute. This is also a riverbed filtration system. This is a project we worked on with Orange County Water District. And you remember that channel, the Santa River I showed you, where they have part of the river that they call the off-river channel, and they're actually able to control the flows in this river channel because they have a rubber dam that diverts it into a pond, and then they flow into here. And so the idea here was, let's remove, it was part of a sediment removal study. They were evaluating different options like coagulation and all types of water treatment to remove sediment. So we came in and we just stuck some slotted pipe in the ground, went to a caisson, and then covered up the pipe. So we have about 3 feet of coarse sand. The groundwater quite shallow in this area. This only works if you have a high groundwater table, because you have to be able to have saturation flow towards your drainage pipes. And this effectively moves 99.9% of all the sediment, which then they send to one of their recharge basins, and allows them to operate much more efficiently, because if they just take water out of the river, it's laden with sediments and clogs the basins. within a few months and then get out there and clean it out. This way they can run, I don't know what the number is, but it's at least a couple years or more longer without having to clean the basins. And the other nice thing is that because they're getting sulfur treatment, it removes about half of the, in only 3 feet, it removes about half the organic carbon, and knocks back the nitrate in the water by about 90%. This is a project we worked on in Oregon, and this is called 50 Mile Creek. And here, what they're doing is they want to get surface water from 50 Mile Creek in the freshet, so that they don't have to divert in the wintertime. I mean, in the summertime, excuse me. But the problem there is that the aquifer they're using for irrigation is deep salt aquifer. So this is designed to infiltrate the water, send it to their ASR wells, the salt. And great on paper design, they had problems with getting approval from the regulators. And so they didn't get approval until like November. And so they were out there and it was wet, it was cold. And the contractor, the engineers that were running it didn't do effective quality control. So they were borrowing from who knows where. It's going in and it's all compacted and the system doesn't work very well. So you gotta be careful with these. It wouldn't work if it'd been actually constructed as everybody thought it would be. Any questions on that? We do have failures. It's good to learn from the failures. So infiltration galleries, these are used basically, let's say you have you have an area where you've got a hard pan that's within 5 feet and ripping it is not good or it's not enough, or you have a big clay layer. And so here you just punch down below the restricted layer, backfill with gravel, and then what it does is it serves conduit to the higher. So you're able to get past lower permeable material and increase the amount of recharge. Depending on what you want these have to be maintained. Clogging is always a problem. Water capture program, and so use filter fabric or like fine sand on top that you can remove the clogs and the catches. So that needs to be considered in the design. And again, this can be classified well, it's not wide enough. So it has to be like, I can't remember, that the bottom has to be wider than what the depth is to avoid it being classified well. Objection.
Okay, so somebody online, you need to mute yourself, please. Thank you.
Thanks, John.
All right, so dry wells. So dry wells is basically a deep infiltration gallery. And typically the whole design of a dry well is basically you drill a deep hole, you put in a perforated casing and a gravel backfill around it, and then you have to maintain a certain level above the water table. And this varies by state. In Arizona, you have to be, I believe, above 20 feet. In Washington, it's like 5 feet. Excuse me, 10 feet. You have to be at least 10 feet above the base zone. And the assumption there is that has to provide some soil aquifer treatment. Now, there's designs to try to remove the sediment. One of the designs is what's called a dual chamber dry well. And basically you have a sedimentation basin that will help. And then you've got to maintain the space and muck out sediment, because every time it rains, you know, you're stirring it up and you're sending it down. Right. The key thing is to try to avoid all the muddy, the gravel that is in here getting clogged with sediment from surface water. Because then you just wasted a bunch of money. But let me see, I think I got a picture of this. This is a caisson rig. This particular rig was made in Italy. It's quite interesting because you know, it pulled up, and this is basically a 4-foot diameter auger It goes down and then they pull it up and dump it out, and then they keep going down and it telescopes. So they don't have to keep changing the mast out. This rig goes actually down to 125 feet. They've got some ones that are deeper, go maybe 150 feet, but you know, once you start it starts getting more difficult the deeper you go. These are used extensively in Washington, Oregon, Arizona. California's starting to drill a bunch as well. Just the Salt River Valley alone probably has 60,000 of these wells. And so it's a real common tool. I know you guys have a bunch of shallow pits in Missoula, or so I read, that are kind of like dry wells, infiltration galleries, capture stormwater. But again, the considerations are, you know, sedimentation control, being above the groundwater table, and then also source control. The city of Modesto had a bunch of what they called were rock wells that they installed back in the 60s, and some of them happened to be upstream of the dry cleaner, and he's dumping the dry cleaning fluid out in his back 40, and now they've got a fairly large TCE plume as a result of the rock wells. So these any type of what I call recharge enhancement that's getting the water down closer to the water table, you need to be considering and doing source control. In Arizona, for example, they don't, they're allowed, I think it's actually a bad idea, that you are allowed to put a dry well that's in a parking lot that may be that's connected to a gas station. But they have to have this special type of absorbent that once it hit, that absorbs the gas, and these things will swell and actually clog the dry well off. Whether or not it works, fortunately, there hasn't been any big spills. This is definitely considered classified USC well, so we have to get that authorization if you do that. And then the thing I just mentioned this already, removal of suspended solids is critical for the life of these wells. Vadosone injection gravity drainage wells. So this is the big brother of the dry well. Okay, so basically this is just a dry well, but now you have a whole injection system. So this is in between a dry well and an ASR well, but you're injecting into the vadosone. So you've got all the pressure head equipment. You also have to have some flow. The name escapes me what they're called, but basically the flow metering control, because once you start injecting water, you need to be able to set it down so that it's not highly agitated and there's a lot of gas that's in train, because if you're injecting water that has a lot of gas in it, you will clog your aquifer sediments, okay, and you'll reduce the efficiency. So this is basically an ASR well, but it's above ground. And it's used where you have, you know, enough of vadosone to handle it, and you don't want to drill another 300 feet, 500 feet, and then go to the additional expense. This is the city of Surprise has a number of these wells. I think it costs about $1,000 per acre foot to recharge with these kinds of wells. So it's quite expensive, and they've been looking at gravity drainage wells, which there's some examples of that in other areas as well that I don't have, but it's essentially the same thing, except they're just back in gravel. Okay, and this is a little stand pipe for monitoring, this they telescoped, they drilled down 120 feet, and they brought it back, and they put in a smaller diameter annulus. And so here they just openly inject the water, and it's infiltrating down like the top of the surface. So they're getting in. They've been able to cut their expected capital and O&M costs. Well, capital costs are similar, except for all the surface, all the pipeline and pumping equipment. But they're with the operation costs, they're coming in around a couple $100 an acre foot to do recharge this way. Again, suspended solids, and with the dry wells, there are some papers that are out, Barroway, thinks that they can help unclog these wells with some of their deflocculants, but they're extremely difficult to backflush treat. So if you screw up your dry well, you're basically, or your bale stone while you're drilling a new well, you can't surge it like you can with a groundwater well and try to clean it up.
Plugging would happen relatively close to the surface, could they just re-enter with drill it? Clean out the sediment? Or-
This right here?
Yeah.
Possibly, but that's not gonna, I mean, this is a gravel backfill, so where the problem with the sediments getting in are gonna be in the formation. And so that's probably not gonna help.
Yeah, it should be, if you can get it plugged
Yeah,
in the gravel patch,
Yeah.
then you could get to it.
these, the water they're putting in here is actually surface water that's been treated to a very high standard and disinfected, and I failed to mention that. These type of injection systems, you also need to be in, disinfecting your water. Primarily because what you don't want is you don't want a bacterial culture growing down in there and clogging it up with that, because again, you're not gonna be able to treat it. I mean, you can hit with some hydrochloric acid, try to knock it out. But this is highly treated water that's going, this isn't stormwater capture, like a dry well that's in a parking lot. ASR storage and recovery wells, this is actually from Los Angeles County. They've got some saltwater intrusion barrier wells that they've been operating for many years. This is just an example. Again, lots of piping, they've got their injection zone. This is one where they're injecting in two different parts of the aquifer that are separated by an aquifer. The recharge water needs to be potable. Anytime you inject into an aquifer, so that it has to be potable, has to be disinfected. Lots of monitoring, greater technical and regulatory requirements, higher capital and O&M costs. So this is the expense of the Cadillac of getting water into the ground. Okay. How are we doing on time?
We've got, we've got about 10 more minutes.
Oh, is that it? Have I taken that long?
They've been asking questions, so.
I'm sorry.
No, you're fine.
Okay, well, I'll go through this because what I'm going to show right now, you guys already know. So, what are the issues, right? So, first one, of course, is hydrologic suitability. You need to have good infiltration rates at the surface of the recharge injection zone. How fast you can put water in is more efficient, more cost effective it's going to be. Are there any subsurface limitations, perching boundaries within your aquifer? How much storage are you going to get out of this? These are all things you have to think about and assess before you go on a project. You need to have somewhere to store the water that you're delivering, okay? And you can do it in irrigation canals. That's one way to do it, is to just be diverting, keeping the irrigation canals wet all the time. But you have to have, you also have to have the infrastructure in place to not only put it in the ground as well as recover it. You're all familiar with this map. Three groundwater regions, basically. We're here in western Montana, and this is the easier. You've got more basin fill aquifers here. This is your geologic map. So this is your Cenozoic, Pleistocene, Holocene period, tertiary, I should say. You're getting into sediments over here, and then you've got all these stringer aquifers that are following rivers, very shallow, narrow, and these are not considered principal aquifers per your classification. Superficial aquifers, so this is going to be where you can get water into the ground, most likely through surface spreading, sometimes to shallow. If you want to do anything in like the Fort Union over in this area, you're going to need to go to some kind of higher technology. Just a couple quick cross sections. One in the western part, and one in the eastern part. Here's your fractured rock aquifers, basin fill aquifers. Again, this is all stuff you know. And then you have these older sediments, they're consolidated sandstone aquifers, confining units. So it becomes much more complex and the cost is going to be greater. I think you wrote this. There's a nice cross section here down by Big Hole. And this is, you can see where it crosses the creek. You get a little bit more sediments here, some older sediments, but this looks like you can get water in the ground. And you might actually be getting water in the ground if there's any ag and irrigation canals. They're occurring off of this as well. Of course, if you go up to Flathead Valley, lots of superficial deposits, a lot of basin fill, but then you have this lacustrine, aquitard there. And obviously it's getting water, but you got to find out where this thing's out if you're going to try to do any type of surface application to increase the recharge. Otherwise, you're going to be into another more advanced subsurface type. So just in general, looking at these methods that we've talked about, the basin fill sediments, there could be all kinds of problems. So you may end up needing to use one of these, right? You might not be able to use surface spread and have to go into your subsurface methods. But once you get into the consolidated units, you're really kind of going to be limited to this. You may be able to find recharge zones, where it's busted up and that if I can do something there, but you're still likely to have to get water deeper down into the subsurface to recharge it. And of course, that's why you need site-specific data, and we'll talk about that tomorrow. Water quality. I want to talk a little bit quickly about water quality. You have to look at the mixing of your source water and the groundwater as well as the receiving zone. Because you may have aquifer zone interactions. If you're in an ag area, you'll have leachable salts. You have to think about that. There's also your geogenic elements, fluoride, nitrate. There's I don't know if it's up here, but in western US, there's pools of nitrate that occurred in the late Pleistocene that have accumulated and they get washed out. So when you start up a recharge basin, these are very high nitrate values. So you have to be aware of that. And then of course, if you are, you may have a lot of oxyanions that if you're continually recharging and you're creating reducing conditions, that may change the arsenic valence, and also that arsenic will become mobile. And so you need to take a look at that. We talked about stormwater capture, high sediment capture, treated wastewater effluent. Talk about this in a minute, but you need to consider pathogens, organic carbon, nutrients, also constituents of concerns. This area could use some surface water recharge, improve the groundwater quality. So this is an example of, this was a pilot project we ran, and we have suctionalized cinders in the Beto zone where we were able to sample. And so at the beginning of the project, very high TDS values. This bulge was due to the agricultural drainage that was there. This was an old carrot farm that got converted into a recharge basin. But over time, basically the salts got flushed out, and actually by the time it got to the groundwater table, the overall TDS didn't. It went up by 150, but compared to what was in the Beto zone, it was not that big effect. And this is the same data, but with nitrate. And you see huge values of nitrate, but eventually they went above. They just approached the regulatory limit, and then after they recharged for enough, it got diluted out. So one of the things we like to do is, if we're looking at water chemistry issues, we'll just take some drill chlorine and we'll flush it in the lab with tap water or whatever the source water is going to be. So this is an example of a bunch of different cores that we took from a monitor well that we drilled, and some had very high EC TDS in it. They flushed out relatively quickly to the very close to the tap water EC. And so that told us that, that there wasn't much going on with this. In this particular case, we took, this was a different project. What we found was that the TDS that flushed out, and this is 4 volumes, mind you. The TDS that got flushed out fairly quickly wasn't that bad, but then there was these spikes. And so this is an example of basically, because you change the chemistry in vadosome, you're getting dissolution of minerals. And I can't remember what the results were. We took some samples and sent them off for those things that point out fluoride, uranium, arsenic, selenium. But this is something that tells you that, well, you have to keep an eye out. There's been more than one recharge facility that has had problems with like flushing out a lot of fluoride, and the fluoride that in the groundwater now is above the drinking water quality standards. Okay, soil aquifer treatment. Soil aquifer treatment is something that we discovered. It's nothing that we invented. Okay, these are all the bugs that live in the soil, and they're going to be there. And they really love organic carbon. That's what they're using as their energy source, their carbon source. And so you can get 50 to 90% removal. We've done extensive literature review on this. 50%, 90% removal of total organic carbon, roughly 30 to 80% removal of things like nitrate and the nutrients. So this is an additional way to clean up the water, like treated effluents. Long demonstrated history. It removes pathogens essentially if there's enough distance. And this is what's going on with RDF systems as well. Constituents of concern like pharmaceuticals, endocrine disruptors. Some of them they take out completely, others for whatever reason are considered recalcitrant. So this is an area where they're continuing to do research. Can you add like some reactive agents into your recharge path that will take out the contaminants of concern? And then, of course, there's a whole issue of PFAS that is coming up as well. So the future of effluent recharge is, I honestly don't know what's going to happen with PFAS, the PFAS regulations, because effluent, all effluent has high PFAS that's most likely above what the new regulatory standards are. That said, everything else that you want to take out, SAT is going to do a reasonably good job of it. It's a sustainable process because it's biological. All right. Are you guys okay with staying for another 10 minutes? I'm sorry, I just rambled on.
Oh, yeah, we're good.
Okay, good. So I just want to give a little case study here because geologically it's, oh, how did I do that? Geologically, it's similar in some areas to what you guys have here in Montana. This is on the border of Washington and Oregon, and this is the Walla Walla River Basin. This is a project we worked on for a number of years for the Walla Walla River Watershed Basin Council, Basin Watershed Council. I always get confused. So what started this is they have steelhead and bull trout as well as Chinook salmon in this river. And it's been over allocated for summer diversions, and they're drying it out in the summertime. And so under the threat of litigation, they agreed in 2000 to maintain minimum flows in the river. In addition, there's been a long-term decline in the average groundwater level in the basin since 1950, with an estimated loss of 20% of base flow house. But they figured, and so they initiated a MAR program. There was a fellow by the name of Bob Bauer who now lives in, I think he actually moved to Laos, but he was living in New Zealand. And he started the MAR program for him. A couple of graduate students at OSU built a groundwater model, and then we inherited the groundwater model. We've been working on the groundwater model since then. So this is the river budget. You know, spring check. They're not, they have quite a bit of water. This is meters cubed per day. These are the irrigation diversions and agricultural demand. And so by the time July rolls around, they're out of sync. And so the diversions and the demand is, the agricultural demand is greater than the surface water supply. So they're basically pumping groundwater at this point in July, which is also contributing to the decline in flow. So their MAR program, basically, they're taking water off that spring freshet, and they've identified, and it's mostly the upper watershed, I'll show them after in a minute. They've identified fields where they can do MAR. They're using this to supplement the irrigation and increase groundwater levels. And in turn, this increases the base flow and minimizes diversions in the summertime. And so their recharge period is from November to May, when there's no agricultural use, but they're then using the irrigation district canals to send water to these sites. So right here, these are all their little basins. What's here in blue. And then I'm just going to show some results from some optimization modeling that we did for them, to look at, well, what if we add more MAR, and we increase like all these purple dots and the green dots, and we increase the amount of MAR that's occurring in the basin. And then they also want to look at some different things in terms of lining the canal and so they can save the money. But the idea that if they're not losing water in the irrigation canal, they divert less. So these are the different scenarios we ran. This is the model layers, basically lots of quaternary and then materials, and then they get into some lower, finer, deeper down, much finer grain units, and most of the groundwater is getting pulled out of these 2 units at the top. And so we used a model called IWFM, which is the integrated water flow model. It was actually developed by the state of California because ModFlow, it does a much better job of surface water groundwater interactions than ModFlow, so they developed their own model. This is the model subregions. And so these are the results. So what we're looking at here is the water balance component. Red is no MAR, current MAR, and that's their existing system. Increased MAR was adding those purple dots, and then the maximum MAR was adding all the green dots as well. So the groundwater pumping goes up. If they stop the MAR, groundwater discharge goes way down, and then this shows you what's going on, increased MAR. And this, of course, is what's going back into the Walla River. Boundary inflow, they're pulling in much more water from outside of the aquifer, of the model domain, excuse me. And then this is how much surface water they end up going to have to divert. So one of the things we found was that the irrigation canals were, well, I'll talk about right here. So conjunctively managing the groundwater and surface water, they can continue on with the MAR, and it's providing water for the irrigators. If they increase the MAR, it's going to potentially increase the summer flow. And the other interesting thing is that if you put water in storage in the wintertime, when it flows back into the creek in the summertime, you have a lower temperature. So for fish like trout, salmonids, they like the cooler temperatures. They really don't handle the hotter temperatures. So that's another advantage of returning water's base flow rather than just reducing water diversions. The canal pipeline, this increases the in-stream water, but it still wasn't quite as good as having the increased MAR scenario. So basically we're saying, yeah, you could line the pipeline, but you don't really need to. You can save money. However, I will say this, they got a bunch of free federal money, so they went ahead and lined a bunch of their canals anyways. And then the maximum MAR scenario was the optimum scenario for them. So my last slide. There's a lot of different ways to get water in the ground. You know, hydrogeologic suitability is going to be your #1 factor, and that's what's going to drive the cost. And then you also have to have the available water supply, and, if you're using stormwater, then you're gonna have to use something to mitigate the sediment so that you don't clog up your basins or your dry wells or whatever. So these are things you need to consider. And you have to have the infrastructure to be able to do it, whether it's irrigation canal, upstream reservoirs, because especially if you're dealing with very flashy things like the sprinkler shed or stormwater, your hydrograph goes up and then it goes right back down. So you have to be able to grab that water somehow. So that needs to be considered. Site-specific studies we'll talk about tomorrow. Be cognizant of potential water quality issues. And again, that's going to depend, especially with the geogenic issues, that's going to depend upon the parent materials for that are part of your beta zone, part of your aquifer. And in the long run, it may not be a problem just due to dilution if you're increasing the recharge in there, but you do need to check it out. And then the nice thing, and this is kind of what I get excited about, is because it's easy to put water into the ground provide for people, provide for farms. I really am interested in how can we optimize this and restore that? Because you know, the dams, I can't speak for Montana because I'm just not familiar with it, but in the Southwest, the dams have just destroyed so much parent habitat and fish habitat because they basically suck the entire Colorado River dry. 25 million feet of water that used to flow to the Gulf of Mexico is now zero. And so it's cool stuff. Any questions?
So the, I guess one of the issues I think we'll have to address in Montana is just we're a prior appropriation state, so it's the water right issue.
Right.
And I mean, in some of these other, like in the Washington, are they a prior appropriation state? And so, it
Yes.
able to get to that conjunctive use
Yeah.
type.
Well, that's interesting because what the I'm not, we got to talk to Jason Keller, River office, that he runs that project. But my understanding is that on the basin, the watershed basin council, there's irrigators and there's various, everybody who's got a stake in the game is pretty much there except for one of the tribes. They've chosen not to participate. And so I think that when they're diverting, they've got some way of allocating whose water is what for the water that's getting recharged. That's my understanding, but Jason would be the best person to comment about that.
Are there questions on Zoom or Teams or whatever? Yeah, I'm not touching it.
Oh, let me see. There's the mouse, there it is. Could you please mute everyone?
Oh, okay, yeah.
Yeah. I guess I could have muted them. I didn't know that. Any other questions?
I guess I have a following question after John, like, we aren't regulatory, but I was wondering if you could speak to like how you've seen like state regulations progress as like the state has come to like accept MARA as a good method.
Yeah. So the reason we started doing MAR projects was that, so Arizona passed the Groundwater Management Act in 1980. And basically, I think it was Muffin Stewart Udall was head of Department of Interior at the time. Arizona was getting all the financing for the Central Arizona project, which pulls water from the Central Arizona and takes it all the way down to Tucson. Now that was part of the water rights that Arizona had under the 1927 compact. And he basically said, we're not going to approve this loan to you until you get your act in order. And so the governor at the time pulled all the players together and knocked heads, and they came up with groundwater management act. And what that did was that basically established what's called active management areas. There was 4 of them originally, now there's 6. And all the active management areas had to basically create what's called insured water supply. And what came out of that was rules for underground storage facilities. And so there had been groundwater recharge already going on in Arizona since the 70s, really, where there was managed aquifer recharge. But that was what drove the adoption of this regulatory scheme for managed aquifer recharge. And so in the 90s through the early 2000s, Arizona built a huge number of very large groundwater recharge facilities, which was also being driven by the fact that Arizona's looking at California taking all their water. He said, hey, they're taking our water. And so they pulled, and I don't know what the number is, but they put 13, 15 million acre feet of water in the ground, something like that. And so there was lots of factors that went into that. So the regulatory scheme in Arizona is quite advanced. It's agreed, everybody plays the game. California's a different story. They didn't pass the groundwater management act until 2015. And so everybody's still kind of scrambling, figuring out what does this all mean, and then the whole water rights issues with that. So I can't speak to Montana, but one thing California has done is they've identified what flood flows are, and basically their rule is if it's above 90%, if you're above the 90% percentile, you can take 20%, don't need a water right for it. And so that somehow gets determined in the permitting process. And so if you have a flood warning facility, and they have huge, big extreme wet years. So they can actually get a fair amount of water out through that without it having associated light. Your question?
No, I was just amused at the idea of us trying to do that while we're in the middle of adjudicating the current.
No doubt. That was
Yeah, we just don't know how to do.
that was an executive order. That was an
We'll have to learn.
executive order from the governor of California. Yeah, and I what authority he has to do that, I don't know. Obviously, he did. Yes.
My question, the water quality stuff is very interesting, something I've been wondering about. But so are those flushing tests you talked about, is that kind of like a standard part of your analysis of like
That's a standard part of what we do.
Okay.
Okay, and it's very simple. It's like if you've got like a split plume sample, you did some auger drilling, you just core and you set up in the lab and you just keep flushing water through it until you get 5, 6, 10 core ones. With sonic core, you're going to impact it because it comes out in this big sock, plastic sock, and but it's mainly to make sure that they understand what's going to happen, and so if you have, and again, the other thing, and I'm not sure I would explain this, is that any type of recharge based design is going to get driven by, or any type of recharge design is how much water you have, right? You only have 1,000 acre feet. You're not going to need a big facility, but you're trying to put 30,000 feet in, you need a lot of land, right? And so you just have to balance that and take a look at how much air you're doing, making sure you're getting that good idea of what sediments you have. And then run those tests to make sure that you're going to be okay. Most of the agricultural drainage projects that I've seen and where there was what we call antecedent or geogenic nitrate, you'll get a spike and then it'll quickly go back towards what the water quality is. And in that case, if you have nearby wells, you have to do what we call area of impact analysis, right? To see, well, who are your neighbors? Do I have a gravel pit that's a half mile away there and a flood out? Well, that happens, he's gonna be quite angry and, you know, probably want to sue you. You know, so you have to do that kind of analysis and look at who your neighbors are, and so. And this could be something that, and again, I don't know what regulatory bodies are here, but. Maybe you supply water to people who are closest to the facility for the first year. If you have, if it's like in a whole ag area. And again, it depends, you know, if they were adequately flushing the salts out of the zone and it's fairly shallow, you may not have a problem at all. But for sure, you want to look at things like uranium arsenic. And make sure you're not releasing any of that, because then that gets exciting.
Because I guess I was curious about, when you're doing it in old ag areas, when we just kind of flushing out what's there, but
Right.
you're doing it somewhere where there's an ongoing like input source.
Yeah, you kind of have to look at parent materials, you know, and see whether they have high arsenic or valium, so.
So do you use like the source water from what you'd be injecting
Yeah,
in that? Okay, so it's not.
yeah, so that source water, or we've used tap water as well. You know, it really depends on how big it is. It's a small facility, tap water's fine. Yeah.
Any other questions? Right. Well, thanks, Mike. We appreciate it.
Sure.
Sure, let me know when you guys figure it out.
Yeah.
Okay. Okay, it's fine.
I'm gonna go in. Yeah. So I can still. Yeah. All right.
I'm sure he'll be.